So we are recording this part of the session, so you have some examples to look at afterwards. So if anybody has any objections with recording, please say so now. Okay, thank you. So we are going to, before we go on to the next topic, I had asked you guys to try to do example 2. Which is the graph of minus 4x squared plus 12x minus 9. Okay, so let's try to do the graph and do everything. Find the information of the function and try to do the sketch the graph for that function. Okay, so I'm going to switch over to the canvas over here. And I would appreciate it very much if somebody could let me know the function, please.
F of x.
Thank you, Viviana. F of x
Equals minus 4x.
Give me a moment here.
Yes.
F of x equals minus 4x squared. Is that correct?
Yes.
Okay.
Plus 12x.
Plus 12x.
Minus 9.
Minus 9. Correct. Thank you very much, Viviana. So let's try to extract some information from this function that we're given, and let's try to sketch the graph. There's a bunch of problems like this one in the homework task that have to do with quadratic functions and doing basically what I'm going to ask you guys to do in the exam, which is basically I'm going to give you a quadratic function and find the intercepts, sketch the graph, find the vertex, etc. So what is one thing that we can identify from the expression just by looking at it that can, yes, go ahead.
That it's a parabola.
Going
that
down.
It's a parabola. That's very important. It's a parabola. Very good. I think, Andrea. What else do we identify?
Since it's minus 4, it's going down.
Correct. Very good, Viviana. So the parabola, it's a parabola because we've got an x squared, and the parabola is facing down, or the vertex is a maximum point because we've got a minus 4 here. Remember that when the parabola is negative, then it's facing downwards. So let's try to manipulate this a little bit. In the end, we want to extract some more information about it. So let's first try to find the intercepts, okay? And let's first find the x-intercepts, okay? How do we find the x-intercepts? Well, what we're going to do is we're going to make this expression equal to 0. So we're going to say that minus 4, we need to find the roots, remember, to find the intercepts. Minus 4x squared plus 12x minus 9 equals to 0. Remember that the x-intercept means finding the roots, okay? And how do we find the roots? Well, we can try to factor the expression, or we can use the general formula. Remember that if we use the general formula directly, we'll always find the roots, okay? I'm going to do some mathematical manipulation here just so we have that recorded. I am going to do here, I'm going to try to find a way that maybe we can factor the expression. Oops. Okay, so what I'm going to do is that I'm going to bring out the minus 4. And this is going to give me minus 4x to the square minus 3x And I'm going to get a fraction here. So this is going to be plus 9 divided by 4. By the way, anybody, while I'm doing this, because this is one method of doing it, anybody, please, or all of you, while I'm doing this, try to find the roots using the general formula. You should get to the same thing I'm going to be getting to here.
Professor, I already had it.
Okay.
The roots. Well, it's only one root.
It's only one root. I'm going to write it down up here, Diego, while I finish this, and so we can verify. Can you tell me which one it is, please?
The root, it's equal to 3/2.
3/2, and it's only one, right?
Yes.
That's important information. Let's leave this here, and that's using the general formula, right, Diego? And everybody knows the general formula expression, right? Okay, thank you very much, Diego. That's perfect. So the two roots, and I'm going to write them down here as x1, 2, are equal to 3/2. Okay, now let's see how if we can get that with the expression we've got down here. And so notice that what we have here, what we've got here is a perfect trinomial, a perfect square trinomial. And this can be factored, actually. Okay. And so this is going to be equal to -4 multiplied by x minus, actually, 3/2 elevated to the power of 2. And how can we verify that? Remember that in a perfect trinomial, we have x to the first component to the square is x squared, then 2 times the first component times the second one, so 2 times x minus multiplied by -3/2, the 2's are going to eliminate and I'm going to get 3x. And lastly, we elevate the second element to the square, so 3 divided by 2 to the square is 3 times 3 is 9, 2 times 2 is 4. So this is equivalent to this. And from here, we get that the roots are x minus 3/2 equal to 0. And that gives us x equals 3/2. So, which is the same thing we got up here with the general formula that Diego calculated. So what does this mean? So this is a parabola, and the two roots that we have are the same. Or what does that mean is that the roots are the two roots are in the same place, or one is on top of the other. And it's an x equals 3/2. So this means that we've got, I'm going to write this down here, 1, 2, 3, and 3/2 is right around here. So that means that somehow the parabola touches that point, okay? Now, the x-intercepts mean that the parabola should be crossing the x-axis, but we only have one point. What does it mean when we only have one point as the x-intercept? It means that the parabola only touches in that point, and that means that there's only one place that the parabola can touch, and that is going to be on the vertex. So something that we can infer right now from this information is that the parabola is only going to touch x in 3/2, and we know that the parabola goes downwards. So the parabola is going to be something like this. And I'm exaggerating the curve here. Okay. It only touches in one point. So actually, part of the problem is solved because the other thing that I just found automatically is the vertex. The vertex, remember, is going to be the point which is either going to be the maximum or the minimum point where the parabola of the parabola. So right now the vertex is going to be here exactly where we have this 3/2. Okay, and I'll get to the questions in the chat in a moment. And again, this is going to happen when there's the situation where only one, when we calculate the x-intercepts, when we only have one x-intercept, that means that that x-intercept has to occur in the vertex. Okay. Okay, give me a moment to answer a question here in the chat. Okay. Now, what other information could be useful? We don't know what this point here is. We don't know what this point here is. What is that point called? Anybody?
The y-intercept.
Y-intercept, correct, Diego. And how do we calculate the y-intercept? We are going to make all of the x's equal to 0 in the expression. So the y-intercept, we are going to make all of the x's equal to 0. So y.
Professor,
Yes, go
question,
ahead.
it won't be -9?
Yes, correct.
We don't need just focus on the -4x squared plus 12x, and the -9 that is there will be the y-intercept always.
That yes, actually, what the y-intercept. This is a good observation that Estrella is doing. And so basically, we're finding f of 0, which is going to be y. And if we look at the original expression here, when x equals 0, this is going to be eliminated, and this is going to be eliminated. So what are we going to be left with?
-9.
The -9 that Estrella is mentioning. So that's correct. That's correct. So basically what's going to happen here is that it's going to be -9. And that's actually, that's also an important observation. That's actually always going to occur. The y-intercept is going to be when x's are 0. So it's going to be the factor that's left alone. Now, if we want to make this a little bit more accurate, this isn't so proportional. So actually what's happening here is, I'm going to erase the parabola. Actually, what's happening here is that, I'm going to exaggerate this a bit. It's going to be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, and we've got 9 down here. So actually, if we want to be a little bit more accurate in our graph, and let's remember things that we saw before. Remember the original graph that I drew? Let's say this, it was a bit chubby. But now I'm noticing, because of the y-intercept, that it's a bit more narrow, it's a bit thinner. Why? Because actually this 4 that we have here is generating, since we're multiplying by the 4, it is automatically generating a stretch in the graph. Okay. And that's why the real graph that we are sketching to be a little bit more accurate should be a bit more stretched towards the bottom. So actually what should be happening, let's see if I can draw this here, is that the parabola is coming downwards and crossing here. And let's go, whoops. So, the parabola is a bit more spiky than what we could have expected. Okay, so we've got the 3/2 where the vertex is, and it crosses in 9. So the parabola is going to be something like that. The section, I believe it's section 2 of homework task, is a bunch of problems like this one. It's basically finding the intercepts, kind of like this, and finding the vertex and doing the procedure that we did on this one and on the previous ones. Okay.
Professor, I have a question.
Yes, please go ahead. I think it was Viviana.
Yes. What is the function f in standard form?
Okay, that's a good question. The standard form, if I'm not mistaken, the standard form is this one. It's the one that has the 3 elements. So remember that in class, okay, we mentioned 2 forms. Okay, remember that we saw the general form that was ax squared plus bx plus c. And then there's the vertex, the one that has the vertex, okay? And so if I'm not mistaken, according to the terminology in the book, I believe this one, I'm sorry, no, this one is called the general form. And the standard form would be with the vertex, if I'm not mistaken. So if we were to write the standard form here, we write it with another color. Then the standard form in this case would be f of x equals minus 4. Write this down in a more horizontal way. I think in the texts that because the problems are taken from the textbook, and you might find differences in different textbooks how they call it. I believe the standard form is when you use the vertex. So it's minus, in this case, it would be minus 4x minus 3/2. And in this case, the vertex, the coordinates for the vertex are 3/2
And 0.
0, correct. And that's congruent with this form here because we don't have anything adding here. So the 2 ways in which we can represent it is this way.
And it's here, right?
Yes, correct. Thank you very much for that. Squared, okay. So the 2 ways in which we can represent it would be this way here, which is basically where we have the ax squared plus ax squared plus bx plus c, and in this one where we've got the vertex, okay.
Okay, thank you.
Okay, questions with this one before we move along?
I have a question.
Yes, go ahead. Estrella, yes, go ahead.
Yes, it's because, for example, if I wanted to do, like we always graph just by looking at the function, what will happen with the plus 12?
What do you mean?
Like, for example, if we have plus 12, we will, what was the word? Shove?
Oh, well, no, Estrella, that's a good question. When we were talking about the power functions, the power functions only have one element that's the highest power and whatever we're adding or subtracting. They don't have the other powers of the function. So to graph this, we need to do this procedure, okay?
Oh, okay.
So for example, if I would have given you 4x squared minus 9, if you look at all of the other examples that we saw with the power functions, it's just the power function, which is the maximum power, and some constant that's being added or subtracted. We don't have anything here in the middle. So for example, at least with the material we saw up to this point, I'm not going to give you problems like this one. So for example, let's say that I'm going to write it in red because these aren't the types we've seen. Let's imagine that I say, I don't know, I'm going to put a very weird example. X to the 3 plus 3x squared plus 9, for example, okay? This isn't like the examples we've seen. Why? Because in the examples we've seen previously, we only have this element and the constant element. We don't have anything in between, okay?
Okay.
So the first cases that we saw, Estrella, are cases where there's a power function and we only have the power function with something that's adding or subtracting that generates the shifts or the reflections. The next thing we're seeing right now, we're seeing a complete quadratic functions where to sketch them, we need to find the intercepts, okay? These functions, for example, if I were to ask you to graph this, which isn't something that we're gonna see, you would need to find the roots and you would need to find a bunch of other things. But these need procedures that are a bit more advanced than you're going to be seeing in other courses.
Okay, yes. That was my question. Thank you.
Okay. Any additional questions before we move on to the next topic? Okay. If not, then I'm going to clear this in. And remember that all of this is being recorded, so you can review it later. Okay, so I'm going to clear this in 5, 4, 3, 2, boom. Okay, and I'm going to switch back to the PowerPoint. Okay. And so the next topic, sorry, that we're going to be covering has to do with combining and composition, okay? And this is actually a very, very simple, not very, very complicated topic. And it has to do when we have functions and we're trying to combine different functions using different operations. And so at least 4 of the operations you're familiar with, which is adding, subtracting, multiplying, and division. But there's another, and these are called combinations of functions, but there's another operation that's called a composition. So a composition is when we make a function out of another function, or where we, a function f is gonna be a function of another function g. Another way or how I like to explain this is that basically we've got 2 functions and I'm putting one function inside of the other one, okay, to create a new function, okay? And so basically for combining and composition, we've got the basic operations here, okay? Oops. We've got the basic operations here, which is basically we've got the addition. So the addition or adding 2 functions, basically we're gonna directly add them, okay? So I've got function 1 and function 2, I'm just gonna add them. The same thing happens for the subtraction. Do these in different colors. So if we got an adding of a function, we are literally gonna add both of them. Same thing happens for the subtraction. So the subtraction of 2 function is literally the subtraction. So this is an arithmetic addition. So either subtracting or adding, we're going to do it that way. If we want to multiply 2 functions, it's basically going to be the product of both of them. And in the case of the division, we're literally going to create a quotient between the 2 functions. But what is the only restriction that we have? the function that's in the denominator cannot be 0, obviously, because that would be generate something that's indeterminate. And if we have two functions f and g, and we're going to be doing the composition of f and g, and the composition is represented by a little circle here. This is the symbol for the composition. Then that means that f becomes a function of g. And basically what we're going to be doing is substituting g within f of x, okay? This is, you're going to be doing this, or you're going to be using this a bit in calculus, in differential calculus. You're also going to be using it, I believe, in integral calculus and multivariable calculus, the composition operation. So it's important for you guys to be familiar with. So let's do some exercises. I believe section 3 of the homework test includes these. Section 4, I'm sorry, includes some exercises of these. But let's do these two examples, okay? So example 3, we've got two functions. We're going to do the composition and do the both compositions. So I'm going to switch over to the canvas over here. And please, if somebody would be so kind as to, I'm going to do problem example 1. Is it 1 or is it 4 or 5? That was 3. If somebody were so kind as to let me know the functions, please. Let me just erase this here. We are doing 3.
The problem,
Yes, if somebody could please help me out, tell me the function f, please.
it says if f of x equals x squared.
Okay, let me write that down. I believe it's Andrea, right?
Yes,
Okay, thank you, Andrea. So f of x is x squared
plus 3x
plus 3x, correct?
plus
Thank you.
1.
Plus 1, perfect. And there's another function that's g of x, right?
Is g of x equals to 2x squared plus 1.
Perfect. Thank you so much. Now, I'm going to do something here just so we can go over it because it's in the homework task, but I'm going to do all of the operations just so you have an example. So the first which would be f. So the problem isn't asking you to do all of them, but I'm going to do all of them just so you have the example because the homework test does. So the addition, so f plus g of x, I'm going to do them in the same colors I used, I think, in the example, would literally be to add both functions. Okay, so how do we add both functions? We're going to say x squared plus 3x plus 1. And we're going to add, that's f, and we're going to add g, which is 2x squared plus 1. Now, for these examples, I'm not going to ask you to completely simplify the expression, but I am going to ask you to do some simplification. So leave it with a mathematical expression that doesn't have terms that haven't, then at least can be added. So what we do here is x squared plus 2x squared is 3x squared. And try to do these while I'm do these in your notebooks while I'm doing this. Then it would be plus 3x plus 1 plus 1 plus 2. That would be the addition. Okay. Now let's try to do the subtraction. So the subtraction would be F minus G. Now the addition, we can, it's the same if we were to add F plus G as if we were to add G plus F, but the subtraction would be different. So be very careful in the exercises. If it says you're subtracting one minus the other, to be very mindful who you're subtracting who from. And so in this case, we would have x squared, which is F, plus 3x plus 1. And then we would have the subtraction of, and it's very important that it's a subtraction of the whole function, and that's why I'm using the parentheses. And so this would give me x squared plus 3x plus 1. And then we would have minus 2x squared. We'll take a break after we've finished this. Minus 2x squared plus 1. Minus 1, I'm sorry. And this in the end would give us x squared minus 2x squared is going to be minus x squared. 3x, that's by itself, it doesn't have any other elements. And 1 minus 1 is 0, so it would be left like this, okay? Okay, we are going to take a 10-minute break and we will resume. I am not going to put the timer on, so I can leave this here because we're going to continue with this example. So we'll take a 10-minute break beginning now. Okay, so we're back now, and now let's do the rest of the operations we've got here. So now if we wanted to do the product of F and G, the product is literally going to be the multiplication of both functions. So it's going to be x squared plus 3x plus 1 multiplied by 2x squared plus 1. And we can directly do the multiplications here. So this is going to be 2x. So I'm just going to multiply each of the terms. 2x to the 4, 2 plus 6x to the 3 plus 2x squared. And then plus x squared. Whoops. Plus 3x plus 1. And we can simplify just adding the terms that are common. So this, I'm going to leave it in the same color. This would be equal to 2x to the 4 plus 6x to the 3. 2x plus x squared would be plus 3x squared plus 3x plus 1. Okay. And next before last, if we wanted to do the division, f divided by g, it would literally be to create a quotient between these two. And it would literally be the division of x squared plus 3x plus 1 divided by 2x squared plus 1. Now here, if there's any sort of direct simplification, we can do it, or we can just leave the expression as it is, as a quotient, okay? So these four would be the four basic operations that we would have, which is adding, subtracting, product, and quotient or division. And now let's look at how the composition would look. So I'm going to use another color for that one. So for the composition, we are being asked, if I'm not mistaken, to find f of g and g of f. So it's going to be two compositions, so I'm going to do them here. So the first is going to be f composition of g which basically means that we're substituting g and putting g inside of f. Now, I'm going to do this here with a procedure that I suggest you can use that procedure, or if you want to do any sort of other procedure that's clearer to you, that's totally fine. But what I'm going to do is the following. I'm going to grab f of x, and I'm going to put parentheses wherever an x is. So I'm going to say that first we've got x squared plus 3 times, in this case, x plus 1. And why am I putting the parentheses there? Because what I'm going to write inside the parentheses is g of x. So we're going to have 2x plus 1 and 2x plus 1. That's how we generate the composition. So basically, we're grabbing g of x and we're substituting it in f of x. That's the composition of f with regards to g. Okay. Now, how would the composition of, and this is A from the problem. Okay.
And the square?
Oh, excuse me, Juan?
Oh, and the 2x plus 1?
Oh, the square, you're right. Thank you very much, Juan. Yeah, that's right, the 2x squared here. Thank you. Good catch. 2x squared. Correct. That would be A, and now B asks us to do the composition of G with regards to F. Now, F is going to be a function of G. So how do we do that composition? I'm going to use the same method. And by the way, I'm gonna finish up here this and the previous one. I just want to put the two examples together. I'm sorry, so we can see the difference. Now I'm going to take G, and G says 2, and wherever there's an X, I'm going to put a parenthesis. And I'm going to substitute the function where the X should be. So in this case, I'm substituting F within G. And so this is going to be X squared plus 3X plus 1. Okay. And so those are both of the compositions that we do. So f of g means we're substituting g within f, and g of f means we're substituting f within g. And literally when we're substituting, we're putting one function inside of the other. And now we can simplify this a bit. We can do a simplification here. And so this is going to be 4x to the 4 plus 4x squared plus 1 plus 3 times 2 is 6x squared plus 3. And so this can be simplified by adding the common elements. So this is going to give us 4x to the 4. 4x squared plus 6x squared is going to be 10x squared, and 1 plus 3 is going to be 4. Okay. And here we can also do a simplification. Okay, and this is going to be equal to, this one's going to be a bit longer. And so let me just, and again, what we're doing here, this is just algebra, by the way. This is just practicing algebra. So what I'm going to do is the following, just to make this a little bit more simpler. I'm going to separate it this way. I'm going to say 2 x squared, and I'm just going to group the 3x plus 1 here. Just so I can do the product a bit easier. I haven't done any operations here. I'm just organizing this. So basically what I've done here is to just group the 3x plus 1 or using the associative law. I'm just grouping I'm leaving the x squared and grouping the 3x plus 1 here. So that way, when I elevate this to the power of 2, I'm going to have 2 that's multiplying x to the 4 plus 2 times 3, I'm sorry, 2 times 3x plus 1 plus 3x plus 1 to the square, and all of this plus 1. So the only thing I'm doing is applying the square of the first one, 2 times the first one times the second one, and the second one elevated to the square. And if we can, and again, this is just again algebra practice. I'm gonna develop all this and multiply it at the same time. So we're gonna have 2. I'm gonna write it down here so we've got a bit more space. We're gonna have 2x to the 4. So I'm gonna multiply by this 2 at the same time. Plus 2 times 2 is 4 times 3 is 12. X. 2 times 1 is 2. Then we've got this element that's elevated to the square. So 3x to the square is 9x squared multiplied by 2 is 18x to the square. 2 times 3 is 6 times 1 is 6x times 2 is 12x. And 1 elevated to the power of 2 is 1 times 2 is 2. And we've got the 1 that's here outside. Again, this is just algebra practice.
Professor, I have a question.
Yes, go ahead, Andrea.
We can leave it without the simplification, right? Or we have to know the answer of what we put inside, like when we substitute it.
Okay, that's a good question, Andrea. So the problem is incomplete if you just leave it like the first part. Okay. So if you just leave it like this with the substitution, it's incomplete. Okay. You do need to get to a polynomial like the ones we've gotten here. The only case in which you can leave it as a quotient is this one. Okay, in the case of the division, but in the case of the composition, you do need to get to the final. You do need to get to the final simplified expression. And when we say simplified, you don't need to factor, you don't need to do anything. You just need to do the multiplications and get a reduced version of the mathematical expression where you've grouped the things that are the same, which in this case, it's what we're going to do here in this last step. So we've got 2x to the 4. We've got 12x plus 12x is, well, let's put them in order. The next one would be 18x squared. Oh, wait a minute. Let me correct something here. Okay, I'm going to erase this part here in the bottom. It's very important for you guys to follow along because I might make a mistake. And the important thing about making mistakes is to recognize that you've made a mistake and correct it. I did make a mistake here. And so I'm going to write this one. I wrote this down a bit mushed up here. And so I forgot to include here in the multiplication, I forgot to include, there's a plus here. And it's 2 times the first element multiplied by the second one. So we've got a 2x squared here that we needed to add. I forgot to add that one. Sorry about that. And so we're going to do this part here again. Since we've got enough space and to generate less confusion, I'm going to first do the interior part. So this would be x to the 4. 2x squared, it's 2 times 3 is 6x squared times x is going to be 6x to the 3. Um, 2x squared times 1 is going to be 2x squared. And then we've got plus 3x elevated to the power of 2. It's going to be 9x squared. 2 times 3x plus 1 is going to be 6x. And 1 elevated to the power of 2 is 1. Plus 1. I noticed that because we didn't have an x to the 3, and that was a bit odd. So let's now do the multiplication and adding. So 2 times x to the 4 is going to be 2x to the 4. Then we don't have any other x's to the 3, so it's going to be 6x to the 3 multiplied by 2 is going to be 12x to the 3. Then we have got, let's see, 2x squared plus 9x squared is going to be 11x squared multiplied by 2. It is 22. X to the square. And then 6x is the only x we've got, multiplied by 2 is going to be 12x. And lastly, the 1 multiplied by 2 is 2 plus 1 is 3. And so this would be the simplified, this would be the answer, the simplified answer. Okay. Now these are examples of the operations of the different types of operations, compositions, etc. And I believe I think it's section 3 or 4 of the homework task has to do with these. Okay. Questions with this one before we do another example? Nope. Okay.
No.
Okay, I'm going to erase this in 5, 4, 3. By the way, the explanation is going to be here in the video, but it's also going to be in the PowerPoint. So I'm going to update the PowerPoint presentation, and the complete solutions are also going to be in the PowerPoint. So you can look at the video, you can take notes. I'm hoping you're taking notes, but you can also see the solution in the PowerPoint. Okay, I'm doing the complete procedure because based on the feedback you guys had given, these in the videos might be useful. So I'm going to clear this. Yes, go ahead, please.
Question. Why is it 9x plus 1? Ah, no, you're adding it on the next one. No, forget it.
If there's something I really, really like is when a student asks a question and then the student answers their own question. That is wonderful, because that means they don't, I am not necessary. And that eventually that's what we want with you guys, for us to not be necessary. Was it clear, Lisa? I'm joking again, please.
Yes. Thank you.
Okay. Any additional questions before we move on? I'm going to clear this in 5, 4, 3, 2, 1. Boom. Can somebody be so kind as to tell me I think example, there's a next example which says example 6. I don't know where we're jumping from 3 to 6. I'm going to check the numbering there.
Yes, it's example 6.
I don't know why, give me a moment here. I don't know why it says 6. It shouldn't. Let me see. I don't know why it says 3 and 6. I'm going to leave the numbering as it is, just so we can reference it. So we don't get more confused. I think the numbering, by the way, I think that the numbering has to do with, because some of these examples are in the textbook, and that's the number of example in the textbook. So I think that's why I left the numbers there. But anyways, let's look at example 6. Can somebody give me I believe it's 2 functions, and they're asking us also for the compositions, right? Yes, okay. So can somebody tell me the first function f of x, please?
It says if f of x is equal to square root of
Okay.
x minus
Square root, perfect.
square root of x minus 3.
Is the minus 3 inside the square root?
Yes.
Okay, so it's x. Oh, my
Minus.
x's are terrible. Oh, my x's are terrible today. X minus 3, okay.
And g of x equal to x squared plus 2.
Okay, perfect. Thank you very much, Estrella. Plus 2. Thank you. And so we're asked to do the f of x. We're just being asked for one composition, f of x. So let's do that. So they're asking us for f of g, I'm sorry, f. So f as a function of g. And I believe they're also asking us to try to identify the domain. So f of g. So that means we're going to be substituting G within F. Okay. So I'm going to do the same procedure I did with the other one. So I'm going to put the square root here, and wherever there's an X, I'm going to put a parenthesis. And so we're going to substitute G with an X. And so now we're going to have an X squared. X squared plus 2. Now, just going back to the question that was asked in the previous example with regards to simplification, we only need to do enough simplification to be able to represent the function. So the only simplification we would need to do here is that we would have the square root of x squared plus 2, and we've got a minus 3 here. So 2 minus 3 is minus 1. So we're going to have the complete function is x squared minus 1. Okay? So that would be the composition. Now, they're also asking us to find the domain of the function. Now, remember, all this is going to come in the exam. This was the first things we started talking about in the first part of the unit. And this has to do, I believe, with, I think it was homework task 4. How do we find the domain? Well, first off, let's see if you guys remember. Because remember, this is going to be a question in the exam. I've said this. Spoilers. I'm literally telling you what questions are going to be in the exam. What is a function? What is a domain? What is a ring? What is a function? How do we define how do we define a domain? Anybody who wants to get that question correct?
The physical values in X.
Perfect, Andrea, perfect. It's all of the possible values that we can have in X for the given function. Perfect. Okay. Now that's perfect answer. Now, what are the restrictions for a domain? What are what are things that can restrict a domain?
The roots. It can be the same number as the roots.
That response is 45% correct. I think it was it Enya? I think.
Yes.
Enya, we're going to stay with you. It has to do with the roots. But what is a restriction with regards to a root?
You cannot have an even root negative.
Correct. Okay. I think it was Viviana or?
Yes.
Viviana, okay. You saved Enya. I was asking Enya, but thank you, Viviana. You can't have a negative number within an even root. Okay. Now, what is another restriction of the domain?
When you have a fraction.
That's, you're almost there. When you have a fraction, but what is the restriction with regards to the fraction?
That it's not equal to 0.
Denominator 0.
The denominator. Okay, correct. So if we have a fraction, the denominator can't be 0. Okay. So in this case, which one of the cases do we have? We have a square root. So if we want to look at the domain, then this part has to be larger than, or is it larger than or larger than an equal?
Larger equal.
Larger equal because it can be 0. So this part here has to be larger than or equal than 0. Okay. And so this actually is a nonlinear function. So what we've got here, we find the roots. The roots for this function are going to be x equals 1 and x equals minus 1. Okay. So I'm gonna try to link up everything that we've seen up to this point. There's a way in which we can find the domain without having to do much calculations, and that's looking at, is it clear that if I were to give you this expression here in the exam, I hope it's clear that you could be able, you would be able to graph it. How would the graph of this one be? Anybody that wants to give it a try, draw it here, please, in the axis that I just drew there, please. Anybody who's brave enough to give it a try. What would the graph of that one be? It's a very simple graph. You guys have already, we've already done a bunch of examples of that. How would the graph of that be? Just the one that I've marked here in purple. Does anybody have an idea as to how to do that?
It's a parabola that's going to touch the x-axis in 1 and -1.
Correct, correct. Is it going to be facing upwards or downwards?
Up.
Up. That's extremely correct. That's extremely correct. So it's going to be going, and I believe it was it Viviana?
Yes.
That's very correct, Viviana. So would you agree that it would be something like this, the function?
Yes.
There's another way of doing exactly the same thing that we just did with Viviana without even having the roots. Is it clear that this is a parabola that's shifted down 1 unit?
Yes.
Okay. Because if that's not clear, then you guys are going to have a tough time in the exam. Remember, we did a bunch of examples of this. So if we've got x squared minus 1, it's a parabola that's shifted down 1 unit. Okay. And so if we want to find the domain for that, for values that are larger than or equal than 0, we have to look at the function and what values are above the x-axis. It's these values here, right? And these values here. And so what would the domain of the function be if we're looking for values that are larger than 0?
Minus.
Yeah.
Oops.
Go ahead. Let's see, Estrella, go ahead.
The domain will be minus infinity and 1, but the 1 is going to be close.
Is it 1 or minus 1?
-1.
Minus infinity to -1, and we would include the 1, but
And then-
we're correct. Go ahead.
I'm sorry, and then it will be 1, and we will include the 1,
Perfect.
and then infinity.
Perfect. Thank you very much, Estrella. Perfect. And so yes, the values are going to be the values that are positive, and those values occur from minus infinite to -1, and from 1 to infinite. And so this is going to be the domain of the new composition function. Okay. So questions with this one? This is basically what homework task 3 covers. No, I'm sorry, homework task 6 is covering. Okay, questions with this one? No. Okay. Before we go, let's look at questions with this one before I clear. I'm going to clear this in 5, 4, 3, 2, 1. Boom. I'm going to go back to the PowerPoint for a moment. And we are going to look at an example here that has to do with composition. That's a written problem. And I know you guys love written problems. You should love written problems. And let's look at this problem here. It says a weather balloon is being inflated with gas. The radius of the balloon is increasing at a rate of 5 centimeters per second. Express the volume of the balloon as a function of time t in seconds. And so this is an example as to how we can do composition using different functions. And I'm just going to go through this example just so you can have an example as to how this composition is applied. Let me just unhide a couple of slides here. There we go. Okay, and so let's see how we could approach this problem using composition. And basically, we're going to be using composition whenever we have more than one function, and we're going to try to relate them. Okay, so again, think about the problem. We've got a weather balloon, and the weather balloon is being inflated. Imagine that you're inflating a balloon. Let's assume that the weather balloon is a sphere, a perfect sphere. And so the radius of the balloon, while you're inflating it, the radius is increasing at 5 centimeters per second. Is that clear? So each second it's inflating 5 centimeters, the radius. So I hope it's clear that if the radius is increasing and you're inflating it, the volume is also increasing, right? So if the radius is increasing at 5 centimeters per second, the volume is also increasing at a certain rate. And I want to be able to find a mathematical expression that represents that. So the first thing we're going to do is that we know that the radius of the balloon is being inflated at 5 centimeters per second. That means that the radius can be expressed as a function of time, and that function would be 5t, meaning t is time, so every time a second or every time 5 seconds passes, the radius increases by, every time 1 second passes, the radius is increased by 5 centimeters. So at t equals 1, we're going to have 5. At t equals 2, we're going to have 10, and so on and so forth. So this is a function of the radius with regards to time. Radius with regards to time. By the way, remember that functions, we're used to seeing functions as f of x. Remember that functions can be anything. And actually the purpose or the reason we use functions is we're trying to represent things that happen in real life with functions. So we're used to f of x, but we can use any sort of variables. Right now we're using radius with regards to time. And a lot of functions are going to be represented with regards to time. Now, the volume of a sphere is another mathematical expression that's given. The volume of a sphere with regards to the radius, so the volume as a function of the radius is given by this expression here, okay? The volume of a sphere with regards to the radius is 4/3 of pi multiplied by the radius elevated to the power of 3. This is a expression for the volume of a sphere. It's something that we can find anywhere, okay? Now, how can we relate these two? Or how can we find an expression, which is basically what I'm looking for? We want to find an expression of the volume of the sphere, but not with regards to the radius. I want to find an expression of the volume with regards to time. So, how could we do that? Well, the way we can do that is doing a composition between these two expressions. So I've already got the radius with regards to time, And I've got the volume with regards to the radius. So if I grab this and put it in here, grab this and put it in here, I can find now an expression that gives me the volume with regards to time, which is what I want. So I know that the balloon is inflating at 5 centimeters per second. I want to know how the volume is behaving. Okay. So let's do that. So if we do a composition of V with regards to R, as we see here, V with regards to R, it means we're substituting R within V. We do that, we find that 4/3 of pi is going to be equal or multiplied by the radius elevated to the 3, but the radius, we know that the radius of t equals 5t. And so we're substituting that and finding a new expression that now has the volume with regards to time. So substituting that, we now have this expression. So now, instead of having the volume with regards to the radius, we now have the volume with regards to time. So now I know, or now I can find out the relationship with regards to how the balloon is inflating with regards to time. Okay, and this is just an example of an application of combining and composition. Okay, questions with this one? Okay, so this section that we saw right now covers combining and composition of functions. And again, I think section 3 or 4 of the homework task 6 is problems relating to these. Okay, and so they're relatively, I think, relatively simple if we understood the procedure. Okay.